Okay, good afternoon, children. In the previous video, we had discussed this relation delta H equal to delta U plus delta Ng RT, where delta Ng stands for number of moles of gaseous product plus minus number of moles of gaseous reactant. Suppose let me illustrate it with an example. Suppose we have a reaction nitrogen gaseous plus hydrogen gaseous arrow 2 NH3 gaseous. If it is balanced, then here it will be 3. So suppose this reaction, gaseous reaction. So what is the value of delta Ng for this? Delta Ng value will be first product moles. How many are there? 2 minus reactant. Reactant is 1 plus 3. So 2 minus 4 minus 2. So when we do numerical, we have to put delta Ng minus 2. Suppose another case I am talking about is, suppose we have CaCO3 solid arrow CaO solid plus CO2 gas. Suppose for this reaction, what will be the value of delta Ng? Now you see this is solid, we don't consider, this is also solid, we don't consider. So there is only 1 mole of gaseous product. So we have delta Ng value. Delta Ng value will be number of moles of gaseous product is 1 and number of moles of gaseous reactant 0. So will be 1. So I think now you are clear. If you get numerical on this, then you can easily calculate. And let me tell you once again, in case of reactions where only solids are involved or only liquids are involved, delta Ng value will be 0, so that delta H will be equal to delta U. So there is a difference in delta H and delta U. Delta H and delta U are different only in case of gaseous system. And in case of solid and liquid, delta H and delta U are same. That is delta H is equal to delta U. Okay, now next topic we are doing is heat capacity. Heat capacity. Now let me first of all give you a concept on heat capacity. Is suppose we have say an object of copper, and say we have here another object, say of another material, say let it be iron. Now suppose both of them have got the same mass, both of them has been heated to same temperature, say both of them is heated to a temperature of 100 degrees Celsius. Okay, yes, so both of them are heated to a temperature of 100 degrees Celsius. Now we have here in two containers, we have say equal amount of water in both of them, same amount of water we have at the same temperature also. Now if we put this copper body here into the water, and if we put the iron body here into the water, suppose initially the water here has temperature of 25 degrees Celsius, 25 degrees Celsius initial water. So when this hot body is kept here, now tell me, what do you think? Will there be same rise in temperature in both the cases? No, temperature will not rise to the same extent. In one case there will be more rise in temperature, in another case there will be more rise in, less rise in temperature. One which has more heat capacity, will give more rise in temperature. One which has less heat capacity will cause less rise in temperature. So this is heat capacity. In heat capacity, naturally, it depends on the nature of the substance. Okay. In the same way, let me give you another example. Is suppose we have copper body and then we have an iron body. Both are having same mass and say both are initially at same temperature, 25 degrees Celsius, and we are heating both of them. And suppose after heating both gets the temperature of 50 degrees Celsius. Both get the temperature of 50 degrees Celsius. Now you see, even if the temperature initially was same, even if after heating they attain the same temperature, now heat gained by both of them need not be same. One which has more heat capacity will gain more heat. One which has less heat capacity will gain less heat. So this is the idea of heat capacity. Okay, now heat capacity, there are two types of heat capacity, very common. One is your specific heat capacity, and in chemistry more important is molar heat capacity. So, what is the definition of specific heat capacity or simply specific heat? You must have read in physics, maybe. Heat required to raise the temperature of a unit mass of a substance through the unit degree, that's called specific heat capacity. I think specific heat capacity value for water, if it is 4.2 joules per gram. Joules, I think, suppose, I don't know exactly the thing, you remember. Suppose specific heat capacity of water, it is 4.2 joules per kg. That means, if we have 1 kg of water, then to raise its temperature by 1 degree, we need to supply 4.2 joules of heat energy. So that's specific heat capacity, and suppose molecular mass of water is 18. Suppose generally specific capacity, suppose this one is, I think, let us consider it in joules per gram. If specific capacity is given in per gram, okay, then if we multiply this by molar mass, suppose 18, if we multiply, then it will become molar heat capacity. So this is a relationship between specific heat capacity and molar heat capacity. So heat capacity or specific heat capacity, if it is given in gram, if you multiply it by molar mass, then we get molar heat capacity. Okay. Now, children, now there are two type of heat capacity in case of gases. There are two types of heat capacity in case of gases. Not so in case of solid and liquid. In case of gas, there are two types of heat capacity that I will be discussing now. One heat capacity is called Cp. Another heat capacity is denoted by Cv. So what is this? It is molar heat capacity. Molar heat capacity at constant pressure and this is molar heat capacity at constant volume. So there are two types of heat capacity for gases. For solid, there is only one heat capacity. Okay. For liquid, there is only one heat capacity. In case of gases, there are two types of heat capacity. Let me first explain why or how there are two types of heat capacity in case of gas. So for that, suppose we have a cylinder. We have a cylinder containing suppose a cylinder which contains 1 mole of ideal gas, and say the temperature of the gas is T. Gas is T. And suppose we are supplying heat. We are supplying heat to this system. We want the temperature of this gas to increase by 1 degree. We want the temperature of the gas to be T plus 1. T plus 1. So suppose this is in Kelvin. So we want the temperature to be T plus 1 Kelvin. So we have 1 mole of gas at T Kelvin. We want to increase the temperature of gas from T to T plus 1. The heat required, is called heat capacity. Now there are two types of process that will be involved here. One is suppose here the volume is made fixed. Okay, the volume is fixed. This piston cannot is fixed at its place. It cannot change. It cannot move the piston. Then the heat required for this purpose, heat required will be Cv. Heat required will be Cv. On the other hand, if this process is carried out at constant pressure, suppose atmospheric pressure outside, that is constant, then when we supply heat in order to change the temperature from T to T plus 1, heat required now will not be Cp. Heat required now will be different, and it is called Cp. And it can be proved that Cp will be greater than Cv. That means heat that will be required to increase the temperature of 1 mole of ideal gas from T to T plus 1 Kelvin at constant pressure will be more than heat required if carried out at constant volume. It is because when we carry out this process at constant pressure, what will happen is the piston, piston will go up. Piston will go up, and there will also be some work involved. Work, PV work will be involved. So, since PV work is involved here, that's why more heat will be required in this case. When we have constant volume, heat that we are supplying is only increasing the internal energy. When at constant pressure, that heat that we are supplying is doing two work. It is increasing the internal energy like before, plus there is some PV work involved. So that's why Cp will be greater than Cv. That is, heat required to raise the temperature of 1 mole of an ideal gas by 1 degree is more than the heat required to increase the temperature of 1 mole of an ideal gas by 1 degree at constant volume. Okay, now there is a small little proof that we can show is that Cp minus Cv is equal to R, that is universal gas constant. So this relation you may be asked to prove in the exam. So what is the proof of that? That I am doing it now. Now you see, heat at constant volume. Heat at constant volume is equal to Cv into delta T. Okay, heat required, is molar specific heat into rise in temperature, that we can write. Similarly, we can write Qp, process at constant pressure will be Cp into delta T. Okay, we have here 1 mole of gas. So this is this relation that we can write. Heat required is given by mass into specific heat into temperature change. Mass into specific heat into temperature change. Here mass is not there because we are considering for 1 mole. We are considering for 1 mole of ideal gas because this Cp is molar heat capacity at constant pressure. This Cp is molar heat capacity at constant volume. Okay, now we have already derived this relation. Qv is equal to your internal energy change. This we have derived, and similarly Qp we also have derived is equal to enthalpy change. Okay, now remembering this relation. H is equal to U plus PV. H is equal to U plus PV. So U plus for ideal gas containing 1 mole of ideal gas, for PV we can write RT, P visible RT. Now for a process we can write this delta H is equal to delta U plus delta RT. For PV we are putting RT, then for a process the change will be like this. Now since for delta H we can write this Cp delta T, for delta U we can write Cv delta T plus here R is constant, so R will come out delta T. Then we can cancel out delta T from both sides, so we get Cp is equal to Cv plus R, so that Cp minus Cv equal to R. So this has been proved. Now if you have a confusion where from this relation has come, let me tell you is that heat gained or lost, it is from this simple concept that mass into specific heat into temperature change. Okay, this is the concept, and from here we have written actually this one. This mass term you cannot see because it is for molar heat capacity. Molar heat capacity, that its value is 1. So this term is here, Cv, and this term is here. So this is a relation, and but you see, okay, in case of solid, or in case of liquid, as I already said, this Cp will be equal to Cv equal to C. We don't have two type of heat capacity in case of solid and liquid, because when a solid is heated or when liquid is heated, there occurs no volume change. This volume change occurs only in case of gas. Okay, so that's why there are two heat capacities in case of gas. One is Cp, another is Cv. I hope it is clear. There you will find in your NCERT book exercise there are some numericals on heat capacity. You should try to do that. Okay, this much for now. Bye bye and have a good day.